is a continuation of the previous lecture. On the previous lecture we already explained the signal operation based on independent variables, and we discussed the two questions from independent variable, how we can transform the independent variable, and how the signal shape or what happens to the signals. Okay. Now we'll continue that problem solving section. After that we will do some problem related to dependent variable. See, there's a discrete time signal, x of n is given, and we need to find out x of n minus 2. So first we will find out x of n minus 2. This is a discrete time signal, and we need to perform the shift operation. Okay, and here you can see that x of n minus 2 means we need to shift the entire signal by 2 units towards right. So it's a right shift, or we can call it as a delayed version. And we can use the mathematical concept to solve this problem. When you do a discrete time signal, we need to take some care because sometimes we will not get a value in the resultant graph. So here you can see that non-zero value starts from 1 onwards. So we can find 1, the index value n, when n is equal to 1. This is x of n minus 2 graph. So we need to find out the 1 will be changed to n minus 2 because transformation is performed on independent variable. So then n is changing to n minus 2. Here n value is 1. So this is the first non-zero value. So 1 is changing to n minus 2. So 1 plus 2 is equal to n. So we will get n is equal to 3. So the value at n is equal to 1 becomes value at n is equal to 3. So you can plot here the magnitude of the signal is 1, 2, 3. And now we can check the second value when index value 2 is changing to n minus 2. So you will get n is equal to 4. So at n is equal to 2, the value is 2. So here that 2 is transformed to 4. So here you can indicate 2. Now you can see that 3, index value 3. So that's 3 is changing to n minus 2. So the new n becomes 5. So at value at 3 is 3. So that value becomes here, and now it is 3. The next value 4, you can plot the index value 6. Again the value will be 3. And after that you can see that 5, the signal value is 0 when 5 is equal to n minus 2, that is n is equal to 7. So at n is equal to 7, the signal magnitude is 0. And similarly for the other values also. So if you observe the graph, you can see that the signal is entirely shifted to 2 units towards right, because the signal is starting from 1, now it is starting from 3 onwards. So this is actually x of n minus 2. Two methods you can use. One is directly shifting by using the concept shift right by 2 units, or delayed signal, or you can use this mathematical concept. Each index value, you can see how they are transformed into new signal. Second signal, second problem is x of 2n. So we need to find out x of 2n. So we need to plot the signal x of 2n here. So for that we can evaluate each point. So the first signal 0 will be transformed to 2n. Okay, that is n is equal to 0. So the same value. Next thing, n is equal to 1. That 1 will be converted into 2n. So n becomes 1 by 2. Here comes a problem, because in discrete time sequence there is no index value called 1 by 2. Initial value is 0, then 1, 2, 3, 4, etc. There is no index value called 1 by 2. So there is no value correspond to n minus, does not exist. Okay. So we will not get any value. So next we will try 2, index value 2. 2 will be converted to 2n. So n becomes 1. So value at 2 is 2. So that 2 will be converted to, or 2 will be transferred to index value n is equal to 1. Okay, so here you can mark 2. Next case, n is equal to 3. 3 will be converted to 2n, so transformed into 2n, so n becomes 3 by 2, that is 1.5. But in the case of discrete time sequence, there is no such point in x-axis, so we cannot mark this index value, so there is no representation for this 2. Now for 3, now we will check the index value 4. So 4 will be transferred into 2n, so n is equal to 2. So you can see that this particular point, okay, at n is equal to 4 will be transformed to n is equal to 2, and here the signal magnitude will be 3. So this is actually x of 2n. If you observe x of n and x of 2n, here you can see some values are missed, and you will get only 2 non-zero values. Okay, and all other values will be 0. That is x of 2n. Now we need to plot x of minus n. It's a very simple thing. X of minus n means simply you will get the mirror image of this particular signal. So you need -2, -3, and -4. Here 0 value is 0. At n is equal to 1, the signal magnitude is 1. So that value will be at -1. Okay. Or you can use the mathematical equation. This is the time reversal operation, or in the case of discrete time signal, it's simply the shift operation. Not shift, it's again time reversal operation. And at n is equal to 2, the signal magnitude is 2, so we can see that it becomes -2. At -2 you will get 2. At -3 you will get 3, because at 3 it's simply 3. At 4 it's 3, so it becomes so this is a discrete time sequence. Or you can try in this way, that is, here this index value 1 becomes -n, so n is equal to -1. So the 1 will be transformed to -1. Okay. Similarly, you can find out each value. The last case, it is x of minus n plus 2. So for plotting x of minus n plus 2, x of minus n plus 2. Okay, there is actually shifting operation and a reversal operation. So we can try this, x of minus n plus 2. So for that we can find out each value. We need to identify the index value 1 in the second graph. So 1 you can equate to n plus 2. So 1 minus 2 is equal to minus n. So n is equal to 1. So it will start from this particular point. Okay, n is equal to 1, the signal magnitude is 1. Now we need to verify that the value 2, so 2 becomes minus 2 plus 2, so n is equal to 0. So the second non-zero magnitude in x of n, that 2 is equal to, the signal value is 2. Now that 2 will be converted to n is equal to 0. Okay, the index value will be 0. So now it is 2. Similarly, you can try the next value, that is n is equal to 3. 3 becomes minus n plus 2. So n is equal to 3 minus 2. So n is equal to minus 1. So you'll get a signal magnitude at minus 1. And the next value will be at minus 2. And from minus 3 onwards, it becomes 0. So if you observe this particular graph, there is actually two operation: time reversal operation, shifting operation. Okay, and in order to perform the signal operation, we need to shift the signal and time reversal operation. So this is basically so if we compare with x of minus n, we already got x of minus n. This x of minus n signal is shifted to unit, right? That is x of minus n plus 2. Okay, this is a negative signal, not x of n, so the concept will be different. X of minus n is shifted 2 unit to the right because it's a time reversal signal. Okay, otherwise you can directly approach the method we followed in this particular problem. Okay, so this is a discrete time signal. When you do discrete time signal, always remember that there will not be any index value that is not integer. So n is equal to 1.5 and n is equal to 0.5 does not exist in discrete time sequence. So in order to find such values, we will use some other method known as interpolation, sampling, etc. That is not included in this particular lecture. Okay. Now we'll move on to the next portion, that is operations on performed on dependent variable. In the case of dependent variable, basically we will perform 5 basic operations: amplitude scaling, addition of signals, multiplication, differentiation, and integration of the signal. So amplitude scaling, don't confuse with the previous one. Previously we performed scaling on independent variable, now is a dependent variable. So if you write the function f of t, uh, t is independent variable and f is dependent variable. And based on the dependent variable, we are performing this operation. So dependent variable amplitude scaling. So amplitude scaling of signals or scaling in dependent variable, not independent variable. So previously we explained scaling operation independent variable. Now we'll discuss scaling operation amplitude. So a signal x of t is amplitude scaled. Scaled means it becomes a into x of t. Okay. So this a into x of t is known as a scaling, and if a is less than 1, we will call it as a signal is attenuated. If a is greater than 1, we will call it as signal is amplified. Okay, attenuated and amplified. So here you can see one signal x of t whose sinusoidal signal whose amplitude is varying from 1 minus 1 to 1. And if you perform a is equal to 0.5 into x of t, so attenuation, so the signal amplitude becomes 0.5 and minus 0.5. Okay, and similarly if a is equal to 1.5, so that is an actually amplification, so amplitude becomes 1.5 and minus 1.5. That is actually amplitude scaling, simply the amplification operation. And when you perform addition operation on signals, not independent variable, dependent variable, that is two signals are added. Here you can see the signal x1 of t and second signal x2 of t, and we need to add these two signals. Means we can add the corresponding amplitude. So if you observe the amplitude from 0 to 1 in the first signal and the second signal. So the first signal amplitude is 2 here. Okay. So 2 is already there. Plus you need to add the signal, which is a linearly increasing signal from 0 to 1. So when it reaches 1, the amplitude is 1. So already signal amplitude is 2. So from 0 to 1, if we take the first signal amplitude is 2 and second one is linearly increasing from 0 to uh, 0 to 1. So the resultant signal will be like this: 2 to 1. Okay, at this particular point 2 plus 1 you will get 3. Okay, when you reach at 1. Now from 1 to 3, okay, from 1 to 3 the signal amplitude is 1 here, and here also signal amplitude is 1. So 1 plus 1 you will get 2 here. Okay, that you can see. And from 3 to 4 the signal amplitude is 2 here, but here it is linearly decreasing. Okay, and here it is 1. So 2 plus 1 you will get 3 here at this particular point. And when it reaches here the signal amplitude is 0 here, here it is 2. So 2 plus 0 you will get 2. Okay, so that will be the resultant waveform. When you perform addition subtraction, corresponding values you can amplitude you can add. Now we'll see the multiplication of the signal. When we want to multiply the signal, same approach that we used in addition we can use. 0 to 1, the signal amplitude is 2 here, okay, and here it is 1. So 2 into 1, that is equal to 2. Now if we consider the signal amplitude from 1 to 2, it's simply 1, and here it is linearly increasing, okay. So the resultant will be the linearly increasing signal, because here the signal magnitude is 1. So you'll get exactly the same signal in x2 of t, okay, linearly increasing. Now from 2 to 3, it's linearly decreasing in first signal, and second signal it is 2. So you need to multiply 2 into this. So at this particular point, you can see that the signal amplitude is 1. So 2 into 1 becomes 3. So sorry, 2. 2 into 1 is equal to 1. But when it reaches signal at 3, here it is 0. So if you multiply with 0, you will get 0. So again, it's a linearly decreasing signal, but slope of the signal will be higher. Okay, because it starts from 2 and it's 3. Okay, this is a multiplication operation. Now we can discuss the differentiation operation. And differentiation and integration operations are very important in the case of signals and system. Normally we will not think about that because how we can perform differentiation mathematical equation, we are comfortable, but on a graphical way it's a new concept. So when perform differentiation and integration, x of t is converted into d by dt of x of t. That is a differentiation operation. So when there is a differentiation operation, in a graphical way, we can say it's simply the slope of the waveform. Okay, you need to find, you need to remember this word slope. Slope means y2 minus y1 by x2 minus x1. You need to simply find this particular ratio, y2 minus y1 by x2 minus x1. That is the slope of the waveform. So derivative of a signal means it's a simply slope. So if you observe the first waveform, you can see that it's linearly increasing, then it's a constant value. Here you can see the amplitude is 8, here 2. From 0 to 2, okay, the amplitude is linearly increasing, and finally it reached at 8. So we need to find out the d by dt of x of t. Okay, so if you observe this particular waveform from 0 to 2, from 0 to 2, okay, if you write x1 y1, it is 0 0, okay, and x2 y2 will be 2 and 8. And if you find the slope in this particular region, slope, it's y2 minus y1 by x2 minus x1. So it becomes 8 by 2, which is equal to 4. That is, slope of the signal is 4 from 0 to 2. So when you find the differential of the signal, y of t is the derivative of x of t. From 0 to 2, you can indicate the amplitude is 4. That's actually the slope of the first waveform. Okay, that's idea. And from 2 onwards, you can see the amplitude is constant. Amplitude is constant means you can see at this particular point, the signal values 2 and 8, and assume that this is the point 3, and 3 itself again it's 3 and 8. And if you find out y2 minus y1, it becomes 0. So slope becomes 0 from 2 onwards. When it's a constant line, slope is equal to 0. So from 2 onwards, you will get slope is equal to 0. So here slope is equal to 4, and here slope is equal to 0. So you will get a square waveform like this. So this is a differentiated waveform. Okay. So when you want to find out the derivative of the signal, simply find the slope of the waveform. On the other hand, when you want to find out the integration of a signal, simply we need to find out the area of that particular region. So we need to integrate minus infinity to t. Okay. So if t, we need to want to find out the value 2. So simply put t is equal to 2. So here there is a signal is given x of t, and we need to perform the integration of this particular signal. Okay. So the resultant signal I can plot here, which is the integral of x of t dt. So integration means simply we'll find the area. So here the signal amplitude is 4 from 0 to 2. So if you want to find out the amplitude of the signal at t is equal to 1, means you need to integrate, this is the point 1, we need to integrate the signal from 0 to 1. So if we integrate the signal from 0 to 1, because assume that this is y of t, okay, uh, if you want the signal amplitude at y of 1, means you need to integrate signal from 0 to 1. 0 to 1, the first signal amplitude is 4 dt, and if you find out this, you'll get 4. Okay, so at uh, t is equal to 1, the signal amplitude is 4. Now if you move like this, if you want to find out the value 2, or you can see that the area of this particular waveform is 4 into 1 is 4. And now we need to find the area of the signal is from minus infinity onwards, minus infinity to 2, 4 dt, because the signal having non-zero magnitude from only from 0, and we need to integrate from 0 to 2. So if we integrate a signal from 0 to 2, it's a square, so area is equal to 4 into 2, 8. Or if you perform the integration, you will get 8, because the signal is only from 0 to 2, 4 dt, so we'll get 8. So at 2, you will get the signal amplitude is 8, so you'll get 8. So you can see that at 1, signal amplitude is 4, at 2, signal amplitude is 8, so it's linearly increased. Now after that, if you want to find out at 3, you can see y of 3, what will be the value. So you need to integrate from minus infinity to 3, uh, the signal x of t dt. But if you integrate from minus infinity to 0, the signal amplitude is, you can split that integration actually. From minus infinity to 0, 0 to 2, and from 2 to 3. Okay. So from this you can see that from minus infinity to 0, signal amplitude is 0, and from 0 to 2, if you integrate, you will get a, and after that from 2 to 3, the signal amplitude is 0, so you'll get 0, and finally answer will be a. So from 2 onwards, if you take any value, the amplitude is always constant, because by using the equation, it from 2 to 3 or 2 to 4, 2 to 5 or 2 to infinity, the last term will be 0, and you'll always get the term a. So this is the integral. Now we can see that integral and differential are vice versa. So we can verify this, okay, by observing the previous forms. You are getting exactly the same waveform. Okay, that about the differentiation and integration. So when you want to find out differentiation, simply find the slope. When you want to find out the integration, simply find the area. Now we'll do one more problem which related to this signal addition, multiplication, etc. So we need to find out y1 of n, which is x1 of n plus x2 of n. So x1 of n is given, x2 of n is given. So we need to add these two signals, that is y1 of n. Y1 of n is simply the sum of x1 of n plus x2 of n. So you need to add simply the two values. At minus 3, no, here it is 0, here also it is 0. So at minus 3 it is 0. At minus 2 it is 0, and minus 1, minus 2. So you will get minus 2. Okay. At minus 1, here it is 0, here it is minus 2. So you will get minus 2. At 0, it is 1 here, and here it is 2. So 1 plus 2, you will get 3 here. So signal amplitude will be 3 here. And at 1, signal amplitude is 2, and here it is 2. So 2 plus 2, 4. So we'll get 4 here. And at 2, the amplitude is 3. Here it is 0. So 3 plus 0 will get 3. Okay, that is a resultant signal. 3, 4 values are 0. So we can draw the corresponding signal. Here it is minus 2, and here it is 0. Because at 4, signal amplitude is 0 here, here also 0. Now 5, 6, 7, there is no value in the second signal, so we can simply draw 2 amplitude. Okay, 5. 7 onwards again 0. So this is the sum of two signals, x1 of plus x1, corresponding values we can add. Now we'll discuss y2 of n, which is 2x1 of n. So here we need to perform y2 of n. Y2 of n is simply 2x1 of n. If 2x1 of n, we don't want to consider x2 of n, simply we can multiply each point by 2. So at minus 2, there is no magnitude, 0 into 2. But at 0, the signal amplitude is 1. 1 into 2, you will get 2 here. So here the amplitude is 2. At 1, it's 2 actually. So 2 into 2, you will get 4. 4 at this particular 4. Okay, sorry, 4, 5, and 6. At 2, the signal amplitude is 3. So 3 into 2, you will get 6 at 0.6. Now 3 and 4, the signal amplitude is 0 because 0 into 2. And 5, it is 2, 6, it is 2, 2 into 2, 4. So you can plot 4 here, here also 4. That is 2x1 of n. Now we'll discuss the third question, y3 of n, which is x1 of n into x2 of n. So now we need to multiply these two signals. So y3 of n is equal to x1 of n into x2 of n. So we need to multiply the corresponding values. So at minus 3, it will be 0. At minus 2, here it is 0. So it will get 0. Here also 0. At 0, here the amplitude is 1 and here the amplitude is 2. So 1 plus 1 into 2, you will get 2. So here the amplitude is 2. And next value at 1, it is 2. Here it is 2. So 2 into 2, 4. So here you will get 4. And next point 3, 2, 3 into 0. So you'll get 0 here. And 3 and 4, 0 here. So you'll get 0, 0. And 5 and 6, the second signal, there is no value. So we'll get 0. So this actually indicating the signal multiplication. Okay. So in this particular question, we explained sum operations, amplitude scaling, addition, dependent variable, and multiplication operation.